In quantum mechanics, we routinely talk about wave functions and how particles can also behave like waves and all that. And we pretend like everybody knows what waves are and what they do. The truth is, though, that this is all that the average person knows about waves. A wave is just what water does at the beach, and it looks like this. Now, if you really want to understand quantum mechanics, this is where we have to start, with waves. This is the first video in a comprehensive series about the path to quantum mechanics, called Quantum Zero. Today we're talking about waves, like what even is a wave? Water waves are the first association people have with waves, but they're actually not that great of an example because they're very particular and also rather complicated. So we're going to start off with a more general description. A wave is a disturbance that propagates through a medium as a delayed response. Or in simpler words, it's a wiggle that moves through something with a delay. A disturbance is a change of something. For example, if you displace water, you get water waves. If you displace air molecules, you get sound waves in the air, etc. This disturbance does not have to be a spatial displacement. It could also be a change in the electromagnetic field, which gives electromagnetic waves, or a disturbance in space-time, which gives gravitational waves, etc. The propagation happens in a causal fashion, through the effect spreading from neighbor to neighbor. There are many good ways to visualize this, like a Newton's cradle or a chain of coupled oscillators. One oscillator influences the next, and this one the next, etc., etc. A medium is something that can wiggle in the first place, so something that is capable of changing and that is connected. In physics, we call this a field. This medium could be water, for example, and if you take some portion of it and you wiggle it, then this effect can spread to the next neighbors and from there further and so on and so on. Or it could be a string that you pluck. So again, you change the position of that one part and this spreads over the whole string. Another super important point here, just because a wave is moving forward does not necessarily mean that the matter carrying it is also moving forward. Sure, it can oscillate around its position a lot, but in total it will either not move at all or just very slightly. An example that shows this beautifully is a grain field moved by wind. The wave moves through the field, but all the grain does is move around back and forth, but it will not change its position in the field. So, the wave is not the water. The wave is what the water does. Also, the medium doesn't even have to be matter. Waves can spread through vacuum, as long as there is some field, like the electromagnetic field. That's why we can see the sun and the stars, because light is an electromagnetic wave and it can move through empty space. Finally, a wave is always a delayed effect, meaning it spreads with a finite speed. Yes, waves have a speed. Within these broad definitions, waves can be a lot of different things. They do not have to be periodical. They don't have to be simply harmonic. Even though that is a simple and very useful case that we will often use. A wave can also just be a singular pulse. Waves are a space-time phenomenon, meaning they're an effect that moves through space and time. If we look at a moving harmonic wave and look at it in constant time, we see this. The wave has a different value at every point in space, and this creates the familiar waveform. If we look at it at a constant point in space, we get this. The location is fixed, but the wave still varies with time. So locally it's just an oscillation. Now, plotting the wave moving through space and also what it does over time at one position, we get similar oscillations. This allows us to define the first characteristics, length and frequency. Length in space is simply how long a wave is, so how much distance there is between two equal points on the wave. This is called the wavelength lambda. Length in time is the duration of one full oscillation, and this is called the period t. We can also measure the inverse of this. Lambda was the distance per wave, but we can also look at how many waves there are per distance. This is called the wave number, or sometimes also the spatial frequency. And the same is true in the time domain, where the period was the time per oscillations. But when we're interested in the oscillations per time, we get the frequency. Both of these quantities are the inverse of the length and exist as either a frequency per unit distance or unit time, or multiplied by 2 pi as an angular frequency omega or angular wave number k. This is just really a constant factor and doesn't change the basic idea. Also, when we look at a snapshot of the wave, this is called the phase at any given point. And at this given point, the wave function has a certain value. This could be an actual height or a pressure or a temperature, depending on what kind of wave we're really talking about. The maximum value of the wave function is called the amplitude. A simple wave like this travels with a certain speed, which is called the phase velocity. We can easily understand how it depends on the other properties by looking at the space-time wave. At this point, a complete wave has moved through, so the distance traveled is the wavelength lambda. The required time for this was a full period t, hence the phase velocity is the distance over time, lambda over t. This can then easily be substituted to other useful relations like wavelength times frequency or angular frequency over angular wave number. How do we describe all that precisely, mathematically? I've already introduced the wave function, and this function contains the full information about the wave. It will give you a value for any point in space at any point in time. Let's use an easy example, a simple harmonic wave. Mathematically, we can write it like this. Or, using complex numbers, like this. Now, this is just the most simple form of wave, and there are many others, and they can be 1D or 2D or 3D, etc. How the particular wave will look depends on the physics behind it, so it makes a difference whether it's a deep water wave or a shock wave or a gravitational wave. Mathematically, this is described by the wave equation. The wave equation is a differential equation, and the simplest and most common form looks like this, which is the same as this, or in 3 dimensions this. This is often called the wave equation, and the key feature is that it relates how the wave changes with time, the second derivative in time, with how the wave changes in space, the second derivative in space. The constant in the equation is related to the wave speed. Note that there are other types of wave equation as well. This, for example, is the equation for capillary waves in shallow water. It looks similar, but it includes the fourth derivative in space. The simple wave function we've already written down is a solution to the wave equation, and if you can do high school level calculus, you can verify that yourself. In fact, any function with the argument kx minus omega t, where k is the angular wave number and omega is the angular frequency, and wave speed is omega over k, is a solution to this wave equation, so we can have any kind of pulse form a wave. Okay, this part of the video was more formal than the rest, so If you're slightly confused now, what you should take away from this are 2 points. First, the mathematical description of what the wave does is called the wave function. And second, this wave function is the solution to a wave equation, which describes the entire physics of the situation. Alright, this should cover all the fundamentals of waves. Coming up in the next video, we'll look at the most important feature of waves, which is interference, so what two waves do when you bring them together. Almost everything else having to do with waves will build on that. So it's the most characteristic and wavy thing. If you have any questions or remarks, please let me know in the comments, and like and subscribe, and see you next time.